Let's now look at some contrived examples to further our understanding of sum and product types. In this example, we are creating a type called status, which is supposed to represent whether something succeeded or failed. Status is a sum type, since it can be either a success or a failure. We define a success using a nullary constructor, i.e. a constructor which does not have any arguments, and a failure with a constructor which takes an int8 argument. The idea here is that if there is a failure, we provide a failure code, which is an int8. Now, int8 is a special version of int which only has 8 bits of precision. We need to import the type to use it, and hence the need for the import statement at the top. Since there are only 8 bits of precision, an int8 value can be any of the 256 integers between -128 to +127 inclusive. Here is an exercise for you. Try to figure out the number of possible values a status can take. How would we actually go about calculating that? Okay, well, status is a sum type, so all we need to do is sum the number of different values the underlying types can take. The first value we know, it can take the simple value of success. Success is a nullary constructor, so it only counts as one value. Then we know it can take a failure. A failure constructor contains an int8 value with it, and we know that the int8 could be any one of 256 integers. So we just need to sum the two, the one from the success and the 256 from the failure, to give us 257. So the status type has 257 possible values. Let's have a look at another contrived example. Here is a data type which we are defining called A, which can be either an A, B, or C. Since there are multiple constructors, we know A is a sum type, and since two of the constructors A and B take parameters, we also know it is a product type. So, now the same exercise for this new type. How many possible values can A take? This one is slightly more difficult than the previous one, so I'll pause for a few seconds. Let's start figuring this out by looking at the first constructor, which is A. Since A takes more than one type as a parameter, we know it is a product. For bool, it can take two values, either true or false. For an int8, we know it can take one of 256 values. So for the product type, to get the total number of values, we need to find the product. Simple really, it's in the name. To find the product, we just multiply 2 times 256. It's 512. So if you have a value with the A constructor, it can be any of 512 values. Now for the second constructor, which is B. This is a product type too, and the number of values which it can take is equal to 256 multiplied by 256 multiplied by 256 multiplied by 2, which is roughly equal to 33.5 million. All we are doing is multiplying each of the possible values each individual type can take. Now for the final constructor, C. It is a nullary constructor, so it can only take one value. That is the value of the constructor itself. And so to get the total number of values which a value of type A could possibly be, we sum up for each of the branches in the union. That's 512 plus 33,554,432 plus 1. So you can see why they are called sum and product types. To find out the possible number of values, you either have to find the product or sum them, or in this case, both. Algebraic data types are types which are formed by combining other types. They are a collection of data constructors. They are called algebraic data types because they form an algebra of types with two primitive operations which we have seen: the product and the sum. We saw this in action in the previous slide, where we were able to use the algebra to calculate the total number of possible values a type has. Quoting from the Scala glossary, we have an alternative definition, which you may find more useful. An algebraic data type is a type defined by providing several alternatives, each of which comes with its own constructor. In the general sense, in Haskell, an algebraic data type will follow the template shown in this code block. We have multiple constructors, and each constructor takes a list of types as parameters separated by a space. The list, of course, could be empty, as is the case for constructor 4. As you have seen, we can combine sums and products to create quite complicated types, but Haskell gives us a nice and simple syntax to define them. The lightweight syntax Haskell provides to define new data types incentivizes us to create a rich model using algebraic data types for our programs. This in turn makes our programs more strongly typed and readable. This video is a clip from a longer video for beginners starting with Haskell. Check that out if you would like to see all of the content. Also check out the entire Introduction to Functional Programming with Haskell course on the Learn channel. See you next time.